Dear students, chemistry is all about molecules, and molecules are made up of atoms. It is always interesting to know how these atoms and thus molecules are oriented in space. In this video, we will have a discussion on a model which helps us to predict the geometry of molecules and thus their orientation in space. And that is valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory is commonly abbreviated as VSEPR theory. It is a model used to predict the geometry or shape of molecules from the number of electron pairs surrounding the central atom. This model was proposed by Sidgwick and Powell in 1940 and modified and extended by Nyholm and Gillespie in 1957. And as the name implies, the main theme of the theory is valence shell electron pair repulsion. That is, the valence shell electron pairs repel each other. And this repulsion forces the atoms to stay as far apart as possible to minimize the repulsion. Minimize the repulsion means the energy will be lower so that it will attain a stable configuration. This arrangement of atoms will determine the geometry of the resulting molecule. So the geometry of a molecule is determined by the number of valence shell electron pairs around its central atom and how these electron pairs stay far apart to minimize mutual repulsion. And that arrangement leads to the geometry of the resulting molecule. Here you can see the electron geometries for species with 2 to 6 electron groups. Here the groups are placed around the central atom in a way that produces a structure with the lowest energy. Lowest energy means with the minimum repulsion. If there are 2 electron pairs, then the structure will be linear. If it is 3, then the preferred molecular geometry will be trigonal planar. And if there are 4 electron pairs, then the preferred geometry or the most stable structure will be tetrahedral. If it is 5, then it will be trigonal bipyramidal. And if it is 6, then the preferred geometry will be octahedral. The lone pair electron domain. Electron domain means the region occupied by the electron that is more spread out or it takes more space than a bond pair. So that means the repulsion between the 2 lone pairs will be more. Why? Because the 2 lone pairs will be very closely spaced because they occupy more space. And hence their repulsion will be maximum. And if it is between a lone pair and a bond pair, then they are slightly far apart and they experience less repulsion when compared to 2 lone pairs. And the repulsion between the 2 bond pairs will be minimum because bond pair electron domains are considerably far apart. So there will be minimum repulsion between 2 bond pairs. So we can say the order of repulsion as lone pair repulsion greater than lone pair bond pair repulsion greater than bond pair repulsion. In this figure you can see that each bonded pair is shared between 2 atoms or 2 nuclei represented as small red balls, and this blue region represents the electron cloud or electron domain. So the bonded pair is shared between the 2 nuclei or 2 atoms. This bond pair is attracted and held tightly by the 2 nuclei. At the same time, a lone pair is localized on the central atom and it is loosely held under the attracting influence of only one of the nucleus. That means a lone pair electron cloud occupies more space than a bond pair electron cloud. And that's why the repulsions between the lone pair is greater than that of the repulsion between a bone pair. And the magnitude of these electron pair repulsions follow the order lone pair greater than lone pair greater than bone pair repulsions. In VSEPR model, a multiple bond is treated as a single bond. That is a single electron pair for deciding the shapes of the molecules. For example, if you have a double bond or a triple bond in a molecule, so that will be treated as a single bond itself. The bond pair size and bond angle decreases with increasing electronegativity of atoms connected to the central atom. The main merit of the VSEPR theory is that it helps to predict the geometries of a large number of molecules, especially those formed by the p block elements. Now let's see how VSEPR theory explains the geometry of molecules containing bond pairs only. First, consider the compounds of the type AB2. For example, beryllium chloride, BeCl2. The central atom is beryllium surrounded by 2 chlorine atoms. The beryllium atom has 2 electrons which forms covalent bond with 2 chlorine atoms. So the number of bond pairs is 2. There are no lone pairs. So in order to minimize repulsion, according to VSEPR theory, the 2 electron pairs stay far apart as possible so that the geometry of the molecule becomes linear. Here you can see that the 2 chlorine atoms are very much extended in order to minimize the repulsion, and the geometry becomes linear with a bond angle of 180 degree. The molecular geometry similar to beryllium chloride, that is examples for molecules having linear geometry are CO2, carbon dioxide, BeF2, HgCl2, etc. Next is the compounds of the type AB3. For example, BF3, boron trifluoride. The number of electrons around the boron atom, which is the central atom, is 3, which forms covalent bonds with the 3 fluorine atoms. So the number of bond pairs is 3. There are no lone pairs. So according to VSEPR theory, the 3 electron pairs stay as far apart as possible to minimize repulsion, and therefore the molecule assumes a trigonal planar geometry, and the bond angle will be 120 degree. BCl3, AlCl3, etc. are some other examples. Next is the compounds of the type AB4. For example, CH4, methane. We know that carbon has 4 valence electrons, which forms 4 bonds with the 4 hydrogen atoms. So the number of bond pairs is equal to 4. There are no lone pairs. So in order to minimize repulsions, methane assumes a tetrahedral geometry as shown here. And the bond angle is 109.5 degree, or you can say 109 degree 28 minutes. CCl4, carbon tetrachloride, ammonium ion, NH4+, are other species which belongs to tetrahedral geometry. Another example that you can see is sulfate ion, SO4 2-. So here there are 2 double bonds, but according to VSEPR theory, for deciding the shape of the molecule, we consider these double bonds as single bonds itself. So that means 4 bond pairs with no lone pair. Therefore, the structure will be tetrahedral with a bond angle 109.5 degree. Now next comes the compounds of the type AB5. For example, phosphorus pentachloride, PCl5. Phosphorus has 5 valence electrons, which form bonds with the electrons of 5 chlorine atoms. So the number of bond pairs is 5, and there are no lone pairs. And the preferred geometry in order to minimize repulsion will be trigonal bipyramidal as shown here. Here you can see that the 3 chlorine atoms are in one plane, while the 2 chlorine atoms are one above and below the plane. So these two chlorine atoms which lies above and below the plane are known as axial chlorine atoms. And these three chlorine atoms at the three corners are referred to as the equatorial chlorine atoms. The angle between the equatorial chlorine atoms is 120 degree. Whereas the angle between any equatorial as well as the axial bond will be 90 degree. And the geometry will be trigonal bipyramidal. PF5, ASF5, etc. are other examples having trigonal bipyramidal geometry. Next, we have the compounds of the type AB6. For example, sulfur hexafluoride, SF6. Sulfur has 6 valence electrons which forms 6 bonds with the 6 fluorine atoms. So, number of bond pairs is equal to 6. Number of lone pairs is 0. The preferred geometry in such a case will be octahedral. The bond angle is 90 degree. Tellurium fluoride, TeF6. Selenium fluoride, SeF6, etc. are examples for species which show octahedral geometry. And the last is the compounds of the type AB7. That is IF7. It is an interhalogen compound of iodine and fluorine. Iodine has 7 valence electrons which forms bonds with the 7 fluorine atoms. The number of bond pairs is 7. Number of lone pairs is 0. And in order to minimize the repulsion, the molecule will adopt a pentagonal bipyramidal geometry. And the fluorine atoms in the pentagonal plane will make a bond angle of 72 degree. And the angle between an axial fluorine atom and a fluorine atom in the pentagonal plane will have a bond angle of 90 degree. Here you can see that there are two fluorine atoms, axial fluorine atoms, one above and the other below the plane, and the remaining fluorine atom lies in the plane of the pentagon. The structure will be pentagonal bipyramidal. So here we have considered the geometry of molecules containing only the bond pairs according to VSEPR theory.